I just had just a kind of a random question about the lab.
I love
Um,
random questions. Yes.
what would be like a real life application or a job that would you would have to test like a strong acid or a strong base? Is that just like a chemical engineering type of jobs, or like why would we?
Um, well, I mean, there's if you were a lot of times, like especially in biochemistry, where you would have to when you've got proteins or enzymes that you're dealing with, they require different enzymes work at different pHs. So some like the ones that in your stomach, um, they have to they have to do their enzymatic reactions at pH like 2 or pH 1.5. Ones that are in the rest of your gut would be at a much higher pH. Ones in your lungs would be at like a more physiological pH, like pH 7.4 or something. So anytime you're proteins or enzymes, you have to make sure that there are no shocks to the pH, because some of them fall apart at the wrong pH, and you might take weeks or months purifying these proteins, and if somehow you're adding a solution to them where the pH changes radically, they might just precipitate, fall out of solution and crash and not work anymore. And so you've spent like weeks or months in the lab and they're gone. So you have to create buffered solutions. And I'm going to talk a little bit more about that. But we sort of talked about it in lab a little bit. But you have to make a solution that is basically pushes back against changes, radical changes in pH. And so that's something that's routine for biochemistry in particular, where pH is extremely important. So yeah, that's if you do any sort of lab work in biology or biochemistry, making sure you have a solution that's at the proper pH for the process you're studying is essential. So that
Okay,
will
thank you.
come up. Yeah, believe me, many
And
many many times.
while you were explaining that, it just popped in my head. Does this have anything to do with when we take Tums or like antacid or something?
Yeah, I mean, if basically that is a buffer you're taking. You're taking uh, something like bicarbonate. That's like the most common, like calcium bicarbonate or magnesium bicarbonate. And what that will do is basically absorb. That's a relatively weak base. And what that does is it absorbs protons um, in your stomach and increases the pH. If the pH gets too low, if you have like way too much acid in your stomach, and the acid that's in your stomach is actually hydrochloric acid. You have cells in the lining of your stomach that pump out hydrochloric acid. It's pretty tough little cells. And so if the pH gets too low, you start to get reflux. And like, if you're an old fogey like me, you get reflux of acid coming out of your stomach and then into your trachea. That's when you get heartburn, because it feels like there's a burning in your chest. That's actually hydrochloric acid from your stomach going in the wrong direction. So you take like a weak base, and what the weak base does, it has a negative charge, the bicarbonate ion, and then it grabs a hold of a proton and turns it into a weak acid. And of course, the weak acid doesn't release the proton like a strong acid would. And it basically binds up a lot of the excess protons and lowers the pH. So yeah, that's exactly what Tums do.
Okay,
They act as a buffer.
thank you.
Yeah. Yeah, a lot of I like to sort of slip in as much, biological chemistry as I can because I think it's the most interesting. But yeah, pH is one of the most critical bits of biology because your body is sensitive to really small changes in pH. Like if your blood pH changes by more than a couple tenths, you get seriously ill. So it's one of the things that like in an emergency they would check to see what your blood pH is, and all the solutions they give you, like saline. You probably heard Ringer's lactate, that kind of thing, like on hospital shows or whatever. That is basically a buffer they're injecting into your bloodstream to make sure that the pH of your blood stays at a very precise, like 7.4 or so, because any big variation from that would be extremely dangerous. So, man, I love a good random question to start the day. Excellent. And we got a bunch more people. Anybody else with a potentially fascinating random question? See, if we were together, we'd be having all sorts of interesting discussions like this, but we still can. Okay, so reminder, we'll have our exam on Tuesday, if I'm not, because a week from today is Thanksgiving, right? Hopefully we're going to be having a relatively COVID-free Thanksgiving. I know we're going to be doing our part. So Tuesday at 9, between 9 and noon, just like we have before, chapters 4, 5, and 6. And we'll be continuing our review, my two groups this afternoon, with basically any topics of those 3 chapters you want to talk about. Chapter 6, pretty much as I've mentioned before, is a review of stuff we've already done, but hopefully covering it in a way that maybe makes a little more sense than it did the first time. And so we left off talking about molecular formulas and empirical formulas. So I sort of just I'll pick up from there, and we'll do a couple of problems together and see how far we get. If we don't get all the way through chapter 6 today, which I don't expect we will, anything that's sort of hanging off the end that we don't get to, I will leave off the exam, okay? Okay. So we talked about empirical formulas, how to derive empirical formulas just based on percent of mass. You would get some sort of indication of percent carbon, percent hydrogen, percent oxygen, and then figure out what is the smallest whole number ratio of those atoms you could put together to come up with that particular combination of masses. That doesn't tell you exactly what the molecular formula is, because something like sucrose is the most common example I think about. It has an even number of carbon, hydrogen, and oxygen. But if you looked at the most basic ratio, it's 1 part carbon, 2 parts hydrogen, 1 part oxygen. But that's not its formula though. It's 6 times that much. So you have to figure out what the mass of 1 mole of this stuff is in order to figure out how much the what the true molecular formula is. So in that instance, we would get the ratios, we get our empirical mass. Oops, let me go back. We would get our empirical mass. Like for instance, with like sucrose, I said we would get that. But then we would have to figure out, well, how much is a mass of 1 mole of sugar? That would be 180 grams per mole. Well, that obviously 1 carbon at 12 plus 2 hydrogens plus 1 oxygen, that's only 40 grams 40, 30. Oops. That's only 30. So obviously there's something's amiss. There's actually 6 times as much carbon and 6 times as much hydrogen and 6 times as much oxygen. So the really important bit of information is the molar mass. And there's lots of historical ways, like, really old timey ways of figuring out what the molar mass is. One of them, and I don't know if we'll get into this later on, one is determining how much, when you add some of your molecule of interest to water, seeing how much it changes the boiling point and the freezing point. That was a way of determining how much a mole was. And there was all kinds of other ways as well that we don't really use anymore because we have much more accurate methods of determining it. So here, there's the example I was talking about right there. So the empirical formula tells you that the smallest ratio is 1 to 2 to 1 carbon, hydrogen, oxygen. That makes sense for the amount of the percent carbon, percent hydrogen, percent oxygen. The thing to remember is that if I was to look at the percent of carbon, hydrogen, and oxygen for the simple and the percent of carbon, hydrogen, and oxygen for the actual formula, you get the same numbers. You just need to know the true molecular mass, or the true mass of 1 mole. So let's do one and we'll see if we can remember how this works. So good old nicotine. So actually this is something that's kind of interesting. In the nightshade family, all kinds of interesting plants in the nightshade family. This is the breakdown when you take a sample of purified nicotine and determine how much carbon, hydrogen, and nitrogen are in there. Now, what was also determined was that 1/4 of a mole of nicotine weighs exactly 40.57 grams. So that was determined separately. So let's use those bits of information and see if we can figure out what our molecular mass is, or molecular formula. So where do we start? Someone help me out. Where do we start with this information? I have this percent carbon, hydrogen, nitrogen. Where do we go from there?
Do we put it into grams?
What do we convert to grams?
The percentages?
Right. So why can you do that? How can you just take a percentage and go right to grams? What's the thinking there?
It's out of 100%. 1 gram per percent. I'm not sure how to explain it.
Well, the idea is if I have 100 grams of this stuff, that's how many grams of each one I would have. So that's just the reason why we pick 100 grams, because that way you don't have to do any calculations. You could make it at 1,000 grams or at 5,000 grams or 10,000 grams. It doesn't really matter. But you need a mass. You need some way to convert this to mass, because a percentage doesn't really help us at all, because there's no units, right? There's no units in a percentage. It's just a fraction. And we need units. If we're going to do any sort of chemical calculation, you need to have units or it's meaningless. So we just assume, let me go back. Damn it, that keeps doing that. So we assume we have 100 grams of this stuff. That means we have 74.02 grams of carbon. We have 8.710 grams of hydrogen, and we have 17.27 grams of nitrogen out of that 100 grams. Okay, so now I got myself some units. What do I do with these units?
74.2 grams carbon times 1 mole over 12.011 grams carbon.
What does that do for us? And what is
to convert it to moles?
Right. Grams, remember, in chemistry, we don't do anything in grams. The only thing we do in grams is actually measure something. Grams don't participate in reactions. Moles do. The molecular formula of something isn't representative of how many grams there are. It's always moles. And so we need to take that many grams of each one of those elements and convert it to moles of each one of those elements, because that is what the ratio is in a formula. So basically, we just look at our periodic table, and everyone has their periodic table in front of them at all times, right? And so 1 mole of carbon is that many grams. So how many moles of carbon is that?
6.16268 moles.
6.162 moles. Okay. And then hydrogen, we want to convert that to moles as well. So, and remember, always have the units in there so we can find out if we're doing this properly. Because the classic mistake is to just say, okay, I got grams, I got moles, and then you just multiply something. And then you come up with some weird number. If you keep the units in there, that will be a guide to show you if you're canceling the right units and are being left with the proper units, then that's the way to actually do the calculation. So when we have moles on top and the units on the bottom, so 1 mole of hydrogen is 1.007 grams. We cancel out grams, we're left with moles, everybody's happy. So how many moles of hydrogen is that?
8.
Around 8.5. 8 point something. 8.1?
8.641.
641 moles.
Moles.
And then nitrogen, again, moles. We look up the mass, and it is 14.007. So remember, we're dealing with atoms, not molecules. So hydrogen is just H, not H2. Oxygen is O, not O2. Nitrogen is N, not N2, because there are atoms in the molecule. So again, grams we get rid of. How many moles do we have? Not going to make Raymond do all of the math, are you? That seems unfair. How many moles do we have? 1.233. Thank you. So we have these weird numbers. So obviously we can't have C 6.2, H 8.6, and 1.2 because you can't have 6.2 of an atom. What do we do with these strange numbers? Divide by the smallest number of moles. Yeah, that's the easiest thing to do. You can like scratch your head and try and figure out what thing can I multiply by that turns them all into whole numbers. I mean, you can do that, but I mean, the easiest thing to do is just take the smallest one, turn that into 1, and see what that does to everybody else. So if I divide everything by 1.233, this becomes, let me change colors so we can see what's going on here. This becomes 1. 8.641 becomes what? 1.233. What's that number become?
7.
7. And what does this become?
5.
1.233. 5. So that's nice. We get all round, even, whole numbers now. That's good. And so we would say so what is this? So C5H7N. What is that?
Empirical?
That's the empirical formula. That is the lowest. The empirical formula represents what is the lowest whole number ratio of atoms that reflects that composition. And it's C5H7N. Now, it might be the molecular formula too. We don't know that yet. So what do we need to do to see what the actual molecular formula is? What additional information do we have to derive the actual formula?
Molar mass.
We need to figure out what the molar mass is. And so what we have that many grams is 1/4 of a mole. So what's the actual molar mass? So 40.57 grams is 1/4 of a mole. What's the actual grams per mole?
$162.28 grams.
Okay, 162.28 grams per mole. So we've got this as our formula. How am I going to figure out whether that's the right formula or not?
Calculate the empirical molar mass.
Right, see how much what's the mass of this? So what is the mass of that? How do we determine that?
Google it.
Google it. You could Google it. But if you don't have a Google in front of you, Ariana came through. So how did you figure that out, Ariana? Add up everything. Need a little more information other than add up everything. So Ariana came up with a mass of 81.12 grams per mole. How do we get that number? Did you Google it? Yeah, look at the periodic table. We see what's the mass of carbon, multiply that by 5. What's the mass of hydrogen? Multiply that by 7. What's the mass of nitrogen? Multiply that by 1. And here you don't even have to be super accurate. You could just say, 5 times 12 is 60. 1 times 7 is 7. And plus 14 is 81. That's close enough, because basically what you want to see is what is the ratio of the molecular molar mass and the empirical molar mass. And right away, you can see that if the molecular is 162.28, that's the molecular, and the empirical is 81. Right away, you can see what the ratio is. The ratio is 2. So what do we do with because the ratio is 2, what do we do now?
Multiply all the vectors by 2.
Right, so instead of C5 and H7, N, now we have C10,
And
14, and 2.
Oh.
So let's see if we get that. Let's see if we did that one right. Yeah. So that's basically a little bit of a review of how we do that. And you can be sure that there's going to be a question like that, not only in this, but on the final as well, because this is a classic kind of chemistry question to get you thinking about moles and grams and formulas and everything else. So this was another thing we sort of rushed through kind of quickly, but I sort of wanted to revisit because one very simple way that scientists have been using for years and years and years to figure out, especially when like oil was discovered and people were trying to figure out what all this bizarre stuff was. Because as you know, crude oil is an incredibly complex mixture of stuff. And so learned early on that if you boiled it or just heated it, and the gases would rise, and then you allowed them to cool. That's like basically what happens in a what's called a cracking tower that you see at an oil refinery. As the gases rise, you cool them down, and then they turn back into liquids. You take that liquid and then you try and figure out what the hell it is. This was one really early way of figuring out what these things were. And so what you would do is you would take a sample of known mass, take like, a gram of it or half a gram, whatever, usually some small amount. And then you'd heat it up to a very high temperature under a stream of high pressure oxygen. So when it combusted, it did so very, very quickly and to completion. You would basically want, if you don't burn something to completion, so here, let's say I have a hydrocarbon, CXHY. I don't know what the ratio of carbon to hydrogen is. And I burn that in the presence of oxygen. If I don't get complete combustion, I don't convert everything to what? What products do I want when I burn a hydrocarbon?
carbon dioxide and
Look at the BMW.
Who's that? I know! I say I like that car. Who's that? This is a copper one. It's just circles.
Okay. So when I burn something, like a hydrocarbon in particular, when I burn it, what products do I want to get at the end? What are the expected products?
Water
Water's one. Mm-hmm.
and
Carbon dioxide.
Carbon dioxide, right. But if you don't burn something to completion, you get a lot of other products. For instance, if you burn wood in your fireplace, you don't get complete conversion. One of the products you're going to get is just carbon. You're going to get charcoal. That's basically what charcoal is. It's just carbon. And so you can burn that again, get a nice charcoal briquette. You can burn that. And it burns with a nice hot flame. You also get carbon monoxide rather than carbon dioxide, because there isn't enough oxygen present to convert all of it to carbon dioxide. And you get all sorts of, weird things forming. So you don't want those, because basically what you want is just water and carbon dioxide. Because if you get just those two, then you can figure out how much hydrogen was there by determining how much water was present, and you can determine how much carbon was there by figuring out how much CO2 is present. If you get all these other things forming, that screws up your analysis. Then you have to figure in, I've got carbon, I've got carbon monoxide, I got to capture all these different things. So that's why you have this very high pressure oxygen at a very high temperature. That ensures you get complete combustion, that all of the carbon gets converted to CO2, all of the hydrogen gets oxidized to water. So that's the reason for doing it under those circumstances. So when you get your carbon dioxide, water vapor, those are your only products, and then you capture them. And I'll show you basically quickly how you do that. You have these collection devices at the end. So you burn it in one chamber, and then the gases pass through these collection devices. One of them collects water. The other one collects carbon dioxide. You test the mass of your collection device before the reaction and then after the reaction. And so the only difference in mass should be the change in mass which accompanies water, and then the change in mass which accompanies CO2. Then you've got a mass of CO2, you convert that to moles. That's how many moles of carbon you have. You convert your water to moles. That's how many moles of hydrogen you have, okay? I think you probably remember that, but this is how it works. So you've got your sample here, and generally you use a fairly small amount. You don't need very much for this to work, because these absorbers are really, really sensitive. And so you're passing in very high pressure oxygen, because again, if there's any oxygen in your sample, basically you don't want that to be reflected in the mass of the water, because you want from the mass of the water, you only want hydrogen from your sample to be in the water. You want to calculate only the amount of hydrogen. So if you overwhelm the amount of water in your sample with atmospheric oxygen, pretty much like 99.9999% of the oxygen in all of these samples is going to come from the atmosphere and not from your sample. That's yet another reason to do this under very, very high pressure. So you burn them, you collect water with something like magnesium perchlorate, something that has something very ionic, that basically so ionic that it captures water out of the atmosphere. So you have something like, super, super ionic like that. It has a very, very high charge. It attracts water to it and doesn't let it go. It basically becomes part of that molecule, with water being basically sucked into the compound. Then you capture CO2 by having a solution of sodium hydroxide. And if in my group who've been doing titrations, you remember that when we were measuring, we were standardizing a solution of sodium hydroxide. One of the reasons we had to do that was because any carbon dioxide that you breathed out or that was in the atmosphere already gets absorbed into that solution of sodium hydroxide, because CO2 will form an acid. It will form carbonic acid when you add it to water. And in the presence of sodium hydroxide, a strong base, it forms even more, it forms even faster. And so basically, if you have a high concentration of sodium hydroxide in there, it basically absorbs all of the CO2 and converts it into carbonic acid. So that takes all the CO2 out of the air. And then you just weigh the magnesium perchlorate before and after. After, there should be water associated with it. You weigh the sodium hydroxide before and after. The additional sodium, the additional mass should be CO2 that you pulled out of the atmosphere. Okay, any questions about how that works? You see how this all comes back, why we had to worry about the CO2 with sodium hydroxide. Basically, the presence of sodium hydroxide pulls even more CO2 out of the air. CO2 will form carbonic acid in water by itself. It doesn't need sodium hydroxide around to do that. But the presence of sodium hydroxide makes that reaction go even faster. So that's why it's even more important to get rid of CO2 when you're dealing with sodium hydroxide solutions. Then you do some good old stoichiometry that everyone knows and loves. So we get our mass of CO2 that gives us moles of CO2, which gives us moles of carbon, because there's 1 mole of carbon for every 1 mole of CO2, right? Then we look at our mass of water, convert that to moles of water. That gives us moles of hydrogen. Now there's 2 moles of hydrogen atoms for every 1 mole of water. So we have to take that into consideration. That gives us a mole ratio of carbon and hydrogen. We can also convert that back to masses and get a percent composition. Either way, basically what we're looking to get is an empirical formula. What is the lowest ratio of carbon to hydrogen we can get? And if there's oxygen in there, whatever mass of sample we put in, we've determined the mass of carbon, we've determined the mass of hydrogen. Whatever's left over has to be either oxygen or nitrogen or whatever else had been determined to be in there. That would be the remainder of the mass. So let's do one together, shall we? So polyethylene. Oh, yes. Question.
Would the nitrogen dioxide react with sodium hydroxide also?
No, you'd have something different to capture that, because basically you convert that to nitrogen. Is kind of a nightmare, because you get nitrogen oxide, you get nitric oxide, you get nitrogen dioxide, you get nitrate, you get all sorts of things. So it's a little more difficult to convert nitrogen to something specific. So basically you just try and figure out how much nitrogen there was and just deal with the hydrogen from water, CO2, the carbon from CO2, and the remainder would be nitrogen. You have to come up with a different way to capture nitrogen.
Okay.
So probably familiar with polyethylene. It's a bag that we're not allowed to use in California anymore. So it makes a very very light plastic that's very, very bendable. Then you get like things like polystyrene, which are much, much harder. But ethylene is a very simple hydrocarbon. And since it's so simple, you can get it to take all sorts of different shapes. And so hydrocarbon, we just consider a hydrocarbon as, like I showed you before, CX, I don't know how much carbon there is, HY. I don't know what X and Y are. So I'm just going to say it's CH something. I pump in a bunch of oxygen, burn it very, very rapidly, and then I collect my CO2 and I collect my water. So here's my sample. Remember, these are really, really small samples. So that is like 126 micrograms, not very much. And then this is how much CO2 we get out of it and how much water. So let's figure out what our empirical formula is. So here's our sample of polyethylene. After we burn it, we get this much CO2, we get this much water. So what's the first thing we want to do with this particular question?
Do we still want to be working with moles?
You always want to be working with moles. Yes, definitely want to be working with moles.
So we would convert each molecule to moles.
Mm-hmm. Yep. So how many moles of CO2 do I have? How do I figure out how many moles of CO2 do I have? Because really what I want to figure out is how many moles of carbon do I have? But I don't have carbon, I have CO2. So all the carbon that was in my sample has been converted to CO2. So this does represent all the carbon that was there. And this represents all the hydrogen that was in that sample as well. So I need to know the molar ratio of carbon and hydrogen. So I definitely need me some moles. Right, so the molar mass of CO2 is around 44. So how do we get, so Ferris, how do I get moles of carbon? So we're going to multiply this by something. I don't divide, Ferris, I never divide. I want to multiply. I want to multiply 1 mole over 44 grams. And it would help if you use the more accurate mass, but we'll see if this works for us. So 1 mole of carbon dioxide is around 44 grams. So how many moles is that? So my grams cancel out, I'm left with moles.
Well, 8.955 times 10 to the negative 5.
Was it 8 point what?
955
10 to the
times
minus
10
5
to the
moles.
negative 5.
Okay. The other thing you could do is like multiply everything by 1,000. So because, you know, you're dealing, so then you don't have to deal with these really, really tiny numbers. Because remember, we're dealing with ratios, so it doesn't really matter. You could multiply them by 10,000 or 100,000 or whatever, if you don't want to deal with these tiny, tiny numbers. So 0.0016 grams of H2O, how many moles is that? What do I, remember, we want moles of water, not moles of hydrogen yet, moles of water. So again, I want to multiply by 1 mole over the mass of water. Right, Ferris, 18. And again, that's a round number, but it may be enough to get us there. So how many, so that's moles of CO2. How many moles of H2O do we have?
.944 10 to the negative 5 times 10 to the negative 5.
Jesus. So I've got, so you can see we have pretty much the same number of moles here. 8.95, 8.94, that's pretty close to the same number. So I could make you could do what you did before, determining the empirical formulas. You just divide by the lowest number. Well, if we divide by the lowest number, we're going to get 1, right? So 1 and 1. So I get 1 mole of CO2 for every 1 mole of water. What is my ratio of carbon to hydrogen?
1-to-1.
Nope. My ratio of carbon to hydrogen is what? You're close, but that's my ratio of carbon dioxide to water. That's not my ratio of carbon to hydrogen, though.
Oh, okay.
You
So
see?
there's 2 hydrogens.
Exactly. So my ratio of CO2 to water is 1-to-1. What's my ratio of carbon to hydrogen?
1-to-2.
1-to-2, exactly. 1-to-2. So there's 1 carbon for every 2 hydrogens. So what is my empirical formula for polyethylene?
CH2.
Yeah, CH2. I just take out the CH2. And that's basically what polyethylene is. It's just a long polymer of carbons with 2 hydrogens on either side.
Professor,
So it's just a
how do
long
you,
repeating. Yes.
how do you know they have a 1-to-1 ratio?
Oh, because the number of moles is the same. Let me go back. So we figured out how many moles of CO2 we had, and we had this number. That's not going to work. You can't see that at all. We had this many moles of CO2, 8.95 times 10 to the minus 5 moles. That was from this amount of carbon dioxide. Then we took this amount of water, figured out how many moles of water we had, 8.94 times 10 to the minus 5. Well, that's basically the same amount. So that's a 1-to-1 ratio because we have the same amount of moles. So you see it's the same number.
So if the moles, they're around the same, they have a 1-to-1 ratio?
Exactly. Basically, remember what we did before is we had, when we did percent composition, we had, this many moles of carbon and this many moles of hydrogen and this many moles of oxygen and this many moles of nitrogen. And to figure out what the whole number ratios were, we just took the smallest amount, the smallest number of moles, and divided everything by that to see if we could convert them to whole numbers. Well, we're doing the same thing here. We take the smallest number, which is 8.944 times 10 to the minus 5. We divide both those numbers by that, and we get 1 and 1. So we have a 1-to-1 ratio of carbon dioxide and water. Because that's what we're looking for. We're looking for what's the molar ratio of carbon dioxide and water. And that is a 1-to-1 ratio because these numbers are the same. I have the same number of moles of carbon dioxide as I do water. I have exactly the same number. That means they're in a 1-to-1 ratio.
I see. Thank you.
Okay, cool. So we have a 1-to-1 ratio of carbon dioxide and water, but there's 2 atoms of hydrogen in water, and there's only 1 atom of carbon in carbon dioxide. Therefore, because I have a 1-to-1 ratio of carbon dioxide and water, I have a 1-to-2 ratio of carbon and the hydrogens in water. 1 carbon for every 2 hydrogens. That means my empirical formula is CH2. And as I was showing up here, that's basically what polyethylene is, just a really long chain of CH2, 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 repeating itself over and over and over and over and over. So let's see if we got that one right. Yeah, CH2, yes.
So the outermost carbons only get 3 bonds instead of 4.
No, they all get 4.
I mean the very outermost.
No, they still get 4. Everybody gets,
Like,
all the carbons get 4. Yeah, they would just be linked to another polyethylene molecule, which would go in the other direction. That'd all be linked together. at some point, yeah, the terminal carbon is going to have like CH3 or something like that. But these chains are so long that you would never notice. The ratio would be, yeah, like 1.2000001 or something like that.
Okay.
Yeah. No, we're not changing the laws of chemistry or anything. Just to make plastic. At least I don't think we are. All right, let's talk about solutions a little bit, because we have dealt with, like I said before, we have done some solution chemistry. We haven't really gone into like what a solution is, how do you make a solution, that sort of thing. But we have been talking a little bit about solutions, concentrations, different ways of talking about concentrations. Here we're going to, in this chapter, we're going to deal with a bunch of different ways to calculate concentrations. Not just molarity, but a lot of other things as well. So solutions are just a homogeneous mixture. That's all it is. Homogeneous mixture of anything. Homogeneous mixture of liquids, homogeneous mixture of gases, homogeneous mixture of metals, of solids. If all the way through it looks completely uniform, that's a solution. So like salt and water. Any point that you take a sample out of a solution of salt water is going to be identical. The same amount of salt is going to be there for if the concentration is uniform all the way through. So the amount, what do we call, there's two parts of a solution. You remember what we call them? There's something that's there in a higher concentration and something that's there in a lower concentration. What do we call the thing that's there in a higher concentration? Like if I have a salt water solution.
Solvent.
Right. The thing that's there in a higher concentration is the solvent. We usually think of that as, that must be the liquid, right? The solvent is the liquid. And what do we call the solid, or the thing that's there in a smaller concentration? So the solvent is there at high concentrations. What's there at a lower concentration? Solute. That's right, Jessica. Solute. But that doesn't necessarily mean that the solvent is a liquid and the solute is a solid. You could have two liquids. Beer is a solution, but you have ethanol dissolved in water. Ethanol is the solute, water is the solvent. They're both liquids, but it's still a solution. One thing to think about.
Is an alloy a solution?
Yes, it is. Yes, it is. And the metal that would be there at the higher concentration would be the solvent, and the metal that would be there in the lower concentration would be the solute. Yeah, as long as it's uniform all the way through, like brass or something like that. With brass is tin and copper. I believe copper is the solvent and tin is the solute.
Okay.
So the solvent is the dissolving agent and is usually the most abundant substance in the mixture, almost always the most abundant. Because generally, if you were to make a solution of something that was so concentrated that the solid was there in a higher concentration than liquid, that's not going to be soluble. So it's almost always the most abundant solution. Air is a solution. You may not think of it that way, but air is a solution. Who's the solvent in air? So air's got, basically hundreds of molecules in it. What would be the solvent?
Is air homogeneous?
It should be. It should be. It isn't always, right? I mean, there could be, like, when the fires were going on, it certainly wasn't homogeneous. There was lots of solids and everything in there, but it should be homogeneous for your health. It should be. So if you were in the hospital and you're getting air, you've got a tank of air. Something's the solvent. What would be the solvent? Oh, nitrogen. Yes, right, nitrogen. 78% of air is nitrogen, and about 20 or so percent is oxygen, and then the rest is, lots and lots and lots of different gases. Interestingly, argon, I didn't realize this till I sort of looked it up. Argon is pretty abundant in air. It's about like 0.5% or 1%. So you're breathing a lot of this noble gas like every day. I didn't realize that. So yeah. So when you have a solution, you need some way to express how much of all these different materials are present. And so we talk about concentrations. And we're used to thinking of concentrations as moles per liter, because that is, chemists use moles per liter probably more than any other means of determining concentration. Why is that? Why are chemists so focused on a concentration of moles per liter? Excuse me. What's the point of that?
Because liquids are usually measured in liters.
Yeah, I mean, yeah, because the metric system says the standard concentration, the standard unit of volume is liters. But why moles? Why don't we just use grams per liter or kilograms per liter, or ounces per liter, or something like that?
That's density.
Yeah, why not just give it in density then? What's the point of why go through the trouble of calculating moles per liter?
To standardize it.
We could standardize it with grams per liter, couldn't we? That's a good point. I mean, yeah, everybody could use the same concentration. Why not grams per liter or kilograms per liter? That would work too. I want you to think like a chemist.
So that's not comparable if two solutions for
Yeah, it's comparable. I could have this many grams per liter of sodium hydroxide, this many grams per liter of HCl, hydrochloric acid. I can compare them. One's more than the other. Why is it so important, moles per liter? What would that do for us that grams per liter can't do?
it shows that the exact amount. I mean the
Grams per liter gives
the-
exact amount. I could give, 3.2267889 grams per liter. That's a very precise amount. So it's not the precision we're looking for.
I mean the amount of the matter.
The amount of matter, well, grams
How
tells
many?
you
How
how
much
much.
of the? How much of the? Well,
Grams does that too. Okay, I'll let you off the hook. I'll give you a hint. When chemists are adding solutions to each other, what are they generally doing with them? What are they looking to do with these solutions? Yes, Nang. You want to explain?
No.
But you've got the right answer. Yes, so Nang points out, because moles are involved in reactions. Exactly. If I have solution A and I want to add solution B to it, the reason I'm doing that because I want to do a reaction. And so if I'm reacting solution A with solution B, grams don't help me. That doesn't tell me how many grams, how many mils, what volume of A I need to add to volume to solution B. What I need is how many reactive units are in a volume of A and how many reactive units are in a volume of B to know how much of each I need to add together to get my reaction to work. And what's a unit, what's a reactive unit? That's a mole. That's why we use molarity, because we don't want to have to, if it was in grams per mole, then we'd have to like convert the grams back to moles and do more math. We haven't got time. We're chemists. We have a lot of important things to do. We got coffee to go get and donuts and stuff. We want to be able to calculate immediately what volume of A and B to use to mix together to get my reaction to work. That's why we use molarity. But there are other ways of calculating concentrations of solutions that are used, and we'll get into those. But a very qualitative expression, like not with units, is dilute and concentrated. We know what that is. Concentrated has a lot of stuff in it. Dilute, not so much. So we take a concentrated solution and then we dilute it to something we can use. And an example is like hydrochloric acid. When you buy hydrochloric acid from a chemical company, generally get like really concentrated solution, like 12 molar. That's super concentrated. Hardly ever do you need that concentration of hydrochloric acid in a reaction. You dilute it because it's kind of a pain. If you needed like, 0.001 moles of hydrochloric acid, it's kind of a pain to measure that small a volume. It's difficult to measure that small of a volume accurately. So what you do, you dilute it. So that's a much lower concentration. And you can measure larger volumes much more accurately. So that's the main reason you do dilutions, is because you can measure them much more accurately than very, very small volumes. So this would be how you do dilutions. If we were in lab, we'd be doing this kind of thing all the time. So if you want to make a very precise concentration, what are these things called? This right here. It's kind of given on the bottom. What do we, these are very special glassware. What are they called?
Volumetric flask.
Yes, it's a volumetric flask. So it's called that because there's a line right there that when you make your solution, you would take enough solid for like 1 mole, precisely 1 mole of solid. You put it in the bottom. You'd add some water to it. Generally, we don't actually do that in a volumetric flask. We would do that in a beaker and stir it so that it all dissolves. That's how you're supposed to do it anyway. And then take the beaker, pour the contents into the volumetric flask, making sure that you don't have a liter, because if you have more than a liter, then you've got to start all over again. So you want to dissolve your solution in less than a liter. So less than. Get all the liquid out of your beaker, and then you take like a squeeze bottle or something, and you slowly add water until it comes to exactly that mark. And basically what you get then is 1.00 liters. So then you would have 3 significant digits of concentration. So as long as you measured your mass accurately, you would have a 1.00 molar solution of KCl or HCl or NaCl or whatever it is. But it's really important when you make this that you use less than a liter and then bring it up to the mark. One of the classic mistakes students make when they're doing this in the lab is that they take, they figure out how much a mole of KCl is, and they weigh that out very, very carefully, and then they add a liter of water to it and mix it up, and then they find out that is, if you do that, if you took a liter of water and added, let's say, 40 grams of KCl to it, what would you expect the volume to be? What would you expect your final volume to be? I'll ask you guys. Yeah, slightly more than a liter. It's not going to be exactly 1 liter and 40 mils, but it's going to be around that. So it's going to be more than a liter because your solid takes up space, and those water molecules have to basically move apart in order to allow your potassium ions and your chloride ions to be present. So that's going to be more than a liter. So then your concentration is going to be less than 1 molar, and then you got to start all over again. So to make an accurate solution, you do it just the very same way I showed before. You would take, and again, they're making this solution in their volumetric flask. Don't do that. But take the exact mass you want, dissolve it in a smaller volume, transfer it to your volumetric flask. And then this is the critical part, is getting the meniscus to be right up to that line. When you get it right to that line, then you've got a precise amount, generally to 3 significant digits, sometimes to 4, if you get like a really good volumetric flask. So any questions about how to do this? It's fun. I mean, it would be nice if we were actually, able to be together and doing this. This is how you would do that. So let's calculate the molarity of a solution. Here's a solution that I used to make all the time. Glycine. It is an amino acid. It's also something called a Zwitter ion because it has both a positive and a negative charge. It has a positively charged nitrogen and a negatively charged oxygen. So we call that a Zwitter ion. It's kind of fun to say. So we've got 0.715 moles of glycine, and we've dissolved it in 495 milliliters of water. What is going to be our concentration? What do we do? What's the first bit of information we need? Actually, we have all the information we need right here. We don't even need to figure out what the molar mass of glycine is. Very straightforward. How do I put these two together to give me molarity? Yep, convert to liters. That's right, Rye. How do I convert my volume to liters? I got 495 milliliters. What do I multiply that by to give me liters? I want milliliters on the bottom, and I want liters on the top. So what's my conversion here?
1/100.
1 over 100?
It's 1,000.
1,000, right? Milli is 1,000. Centi is 1 over 100, like centimeter. Generally, with volume, we deal with thousands. So milliliter would be 1 over 10, 1 over 1,000. Micro is 1 over 10 to the 6th. Nanoliters is 1 over 10 to the 9th, and so on. It's like units of 1,000. So how many liters do we have here?
0.495.
Yeah. And if you want to take the shortcut, since it's 1,000, it's 3 times or 10 to the 3rd. We could just move our decimal point 3 places. Go 1, 2, 3. So this is how many? We have 0.495 liters. So what's my concentration? I have that many liters, I have this many moles. What do I do with that information? How do I put those two things together to give me molarity?
0.715 over 0.495 liters.
Yeah, moles on the top, liters on the bottom. So what's my final concentration?
1.44 forever.
So how many significant digits do I use?
1.44.
3, right. I got 3 significant digits here. I got 3 significant digits in my mass, and my number of moles. And what do I put down as units for my concentration?
Capital M.
Capital M. Yeah, we'll see there's also a small m for a concentration called molality, which I'll sort of mention briefly. That is used for something different. Okay, one more thing. Yeah, 1.44. So let's quickly do this one. So I have this much KCl, potassium chloride. I have 250 milliliters of solution. Now I want to figure out my molarity for this one. So we'll do this one and call it a day. So so now I don't have moles. I have a mass and I have a volume. So what do I do in this situation?
Convert grams to moles.
Right, I want to convert my grams to moles. So I have 9.35 grams of KCl. I want to multiply it by something to give me moles. How am I going to do that? What am I going to look up?
The molar mass.
Yeah, you can either go to your periodic table, get the mass of potassium and add that to the mass of chlorine, or you can just Google KCl. Either one, as long as you get the right answer. So, what's my molar mass of KCl? $74.55. Man, Raymond, quickly. So what do I do with? So it's 74.55 grams per mole. What do I do with that information? So I put 1 mole on the top because I want moles at the end, and I put my mass at the bottom, 74.55 grams. Grams cancel. I am left with moles. That is what I want. So how many moles is that? 0.125 moles.
Do you
Okay.
need more accuracy?
Excuse me?
Do you need more accuracy since it's not the final answer?
Well, I mean, you can put more significant, you can put more digits there. They won't be significant, but yeah, you can include more digits.
I mean, this is not the final
That isn't the final answer. No,
answer, right?
no. Yeah, so I probably wouldn't round to that's a rounded answer, right?
Yeah, rounded answer. The answer would be 0.1254.
Yeah. Okay. Let's put the 4 in there as well. So, yeah, because you don't want to round until you get to the final answer. So we have 3 significant digits in our volume, and we have 3 significant digits in our mass. So our final answer should have 3 significant digits, but that doesn't mean you round early. Remember, I always whine about this. Carry as many digits as your calculator will allow you all the way through till you get to the final answer, and then round down to 3. So that's how many moles we have. This is our volume. What's going to be our final concentration? How do we determine it?
Convert volume to liters first.
Okay. How many liters is that?
That is 0.50 milliliters.
Yeah, so just like 495 mils was 0.495 liters. Same thing here. So we have 0.250 liters. Important that you keep that 0 there because it has been measured. It is a significant digit. So what is my final concentration? And what's the unit? Yep. Aaron, use as many as you want. You don't have to write them all down but I would write down at least for this, I would write down at least 4 or 5 for the moles and then carry that over. So what's my final answer? I've got this many moles. Whoops. I got this many moles in that volume. What's my concentration and what are my units?
.502 molar.
Molar. So that's moles divided by liters. That is molarity. And you get 0.502. So what are the rest of the digits? It was 0.518. Is that
0.50167
Okay.
6727.
167, blah, 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 blah. Yeah, and so you've rounded that 1 up to a 2. And what are my units?
Capital
Molar.
M.
Capital M or moles per liter. They are the same thing. Either way, you can put it as a capital M or leave it as moles per liter. Either one is correct. Okay. So we will pick up next week with looking at different ways of calculating concentrations. You find a lot of them in the hospital, actually. Where grams per liter and percent mass in volume and all kinds of different stuff are used, and parts per million, parts per billion, and stuff like that. And that'll be pretty much it with solutions. So any questions about what we went through today, or what we're going to do this afternoon?
Yeah, Professor. So are these type of questions going to be on the exam?
Yep.
Okay.
Yeah, you can count on calculating solution concentrations and take that to the bank. You know, of course, remotely. All right, anybody else? All right, I will see you this afternoon. There may be a small chance that the review will be delayed by like half an hour or so. I have to take my son to the ophthalmologist, but I think we should be done in time. If we're not going to be done in time, I'll send a note in Canvas saying we'll be a little delayed. Okay?
Okay.
All right. So have a good afternoon, and I will talk to everyone soon, if not sooner. All right. Bye-bye, everybody.